America is building a factory so large it is reshaping a desert. It sits north of Phoenix. 6 semiconductor fabs, 2 advanced packaging facilities, 1 research center. Total announced investment, $265 billion. The largest foreign direct investment in a greenfield project in American history. Every chip foundry in the world is watching. This factory exists because of what happened in 2020. A pandemic froze global supply chains. Car plants shut down for lack of chips. Hospitals waited months for medical devices. One missing semiconductor halted billion-dollar production lines. The world ran on chips it could not make fast enough. America held 37% of global semiconductor manufacturing capacity in 1990. By 2020, that number had collapsed to 12%, falling to 10% by 2022. Every industry felt it. Every engineer took notice. TSMC makes the chips inside your phone, your car, your data center. A large majority of the world's most advanced semiconductors are manufactured in Taiwan. One seismic event, one geopolitical crisis, one supply disruption. The entire global technology economy faces severe disruption. That concentration of risk is what drove this project. Arizona was chosen in 2020. The original commitment was $12 billion. One fab. That number has since grown by more than an order of magnitude. Now watch what they are actually building here. A phased campus planned around 6 logic wafer fabs, with 4 fabs now in production or some stage of construction. The site covers more than 1,100 acres of desert floor. Before one machine enters, the ground must be prepared. Arizona desert soil is not semiconductor-grade land. Geotechnical teams drill test bores across the footprint. Soil-bearing capacity tested throughout the site. Vibration isolation engineered into critical foundation structures. A fab floor must limit vibration to extremely narrow, tool-specific tolerances. Excessive movement can disrupt precision processes and reduce the yield of an entire wafer batch. Zero tolerance. But the scale is not visible from the outside. A semiconductor fab is a building wrapped around another building. Utility corridors beneath the floor. Mechanical levels above the clean room. Pipes stacked in layers. Water, chemicals, vacuum, exhaust, nitrogen, process gases, cooling lines, electrical systems. Thousands of connections feeding thousands of tools. What looks like one factory is actually a vertical network of manufacturing systems. The clean room is only the surface. The machinery supporting it fills the space above, below, and around every production line. Here is the brutal truth about semiconductor manufacturing. The chips being made here are measured in nanometers. A human hair is roughly 80,000 nanometers wide. TSMC's most advanced production process is 2 nanometers. The factory building those chips must be engineered to isolate tools from minute environmental vibrations. Temperature and humidity are controlled within narrow, process-specific limits. Particle counts near absolute zero. A particle landing in the wrong place can destroy a chip. This building does not just house manufacturing, it is the manufacturing environment itself. Before one tool is installed, the concrete work alone takes years. Fab floors are not poured like normal slabs. They are engineered structures, thick and heavily reinforced in critical zones, with foundations designed around the vibration requirements of individual tools. Large sections may require carefully planned, continuous concrete pours to minimize structural discontinuities. The engineering obsession is absolute. The pour can run 24 hours without stopping. Hundreds of workers, every truck timed to the minute. Now the mechanical systems. A single fab can use as much electricity as a small city. A large advanced fab may require hundreds of megawatts of electrical capacity, depending on its size, equipment, and operating level. 6 fabs running simultaneously require dedicated power infrastructure. New substations built specifically for this site. High-capacity electrical connections running directly into the campus. Power quality monitored in real time. Even brief voltage disturbances can interrupt sensitive manufacturing processes and force equipment to shut down. Equipment worth well over $100 million per unit. Sensitive to electrical noise measured in millivolts. Backup power systems layer over backup power systems. Nothing stops. Heat is another enemy. Every tool generates it. Every pump generates it. Every electrical cabinet adds more. Cooling systems must remove that heat continuously without disturbing the environment around the wafer. Chilled water circulates through the facility. Heat exchangers operate around the clock. Exhaust systems capture chemicals and process gases before they leave the equipment. Sensors read pressure and flow across the network. One abnormal reading triggers an alarm. One alarm sends technicians into motion. The factory does not wait for a failure. It searches for the warning before the failure begins. Ultra-pure water is the other critical resource. Semiconductor fabrication consumes millions of gallons daily, every ion removed. Resistivity measured at up to 18.2 mega-ohm centimeters. That is chemically pure water. Contamination is controlled down to parts per billion or even parts per trillion levels, depending on the material and process. TSMC uses in-house water recycling systems and is constructing a major industrial water reclamation plant, scheduled for completion in 2028. Recycling systems recover and repurify water continuously. Arizona is a desert. Water efficiency here is not optional. It is an engineering constraint. The clean rooms themselves are extraordinary structures. The most sensitive process areas and enclosed tool environments can approach ISO Class 1 conditions, with particle limits defined by particle size. For reference, outside air can carry millions of particles per cubic meter. The entire ceiling is a filtered air supply plenum. Cleanroom air is recirculated continuously at very high rates. Workers wear full body suits, gloves over gloves, every material entering the cleanroom tested for contamination. A single human hair can release thousands of contaminating particles. The engineers design people out of the process wherever possible. The photolithography tools are the heart of it. Extreme ultraviolet machines. Depending on the model, an EUV system can weigh well over 100 tons and cost roughly $180 million, while the newest high-NA systems can cost more than $350 million. Only a few hundred EUV systems have ever been shipped worldwide. TSMC operates one of the industry's largest EUV fleets. They use light with a wavelength of 13.5 nanometers. That light is generated by firing a laser at tin droplets up to 50,000 times per second. The entire optical path operates inside a vacuum. One vibration, one stray particle, one uncontrolled thermal excursion. The wafer batch can be compromised. Installing these tools is its own engineering challenge. Each machine arrives disassembled in multiple shipping containers. Specialized rigging crews move the components into the building through purpose-designed access openings. Some fab structures use removable roof or wall sections to accommodate oversized equipment. Tools are then assembled inside the clean room by certified technicians. Calibration can take months per machine. First wafers run as qualification, hundreds of them. Measured, analyzed, rejected, adjusted, again, until every parameter is within spec. Only then does production begin. But lithography is only one step. A modern chip can pass through hundreds or even thousands of individual process operations. Material deposited one atomic layer at a time. Patterns exposed. Material etched away. Surfaces cleaned. Ions implanted. Metal connections formed. Each layer aligned with the one beneath it. The wafer moves back and forth across the fab for weeks. One chip design repeated hundreds of times across its surface. At the end, the wafer is tested. Good dies mapped, bad dies marked, yield measured. Every fraction of a percentage point matters. The workforce challenge rivals the engineering challenge. 6,000 direct jobs are expected from the first 3 fabs. Tens of thousands more in construction and supply chain. Arizona lacked enough semiconductor process engineers. TSMC partnered with Arizona State University and other Arizona colleges and training institutions. Programs were expanded to prepare students and technicians for semiconductor manufacturing. TSMC employees and trainees have also traveled to Taiwan for advanced operational training, returning with skills that did not exist in Arizona before. That knowledge transfer is the hidden infrastructure of this project. The supply chain is being rebuilt around the facility. Semiconductor manufacturing requires hundreds of specialized suppliers: chemical suppliers, equipment maintenance firms, wafer material producers. Many critical manufacturing suppliers and capabilities have historically been concentrated across East Asia, although major suppliers also operate in the United States and Europe. TSMC's Arizona presence is pulling suppliers westward, some building their own facilities nearby. A semiconductor ecosystem forming in the desert. The fab does not function alone. It anchors an entire industrial cluster. Every supplier must meet the same rhythm. Chemicals delivered at the correct purity. Spare parts available before a tool fails. Gas systems inspected before production begins. Maintenance crews trained on equipment built by companies across the world. The campus may be located in Arizona, but its supply network stretches across continents. Building resilience does not mean cutting the factory off from the world. It means creating another center of production strong enough to keep operating when one part of the world is disrupted. The CHIPS and Science Act provided $39 billion in federal manufacturing incentives. TSMC received an award of up to $6.6 billion in direct funding, along with access to up to $5 billion in loans, tied to construction and production milestones, job creation benchmarks, investment and workforce commitments. The government did not just write a check, it structured conditions around the investment. TSMC also committed to advanced packaging capacity and expanded research and development operations as part of its broader Arizona investment. Every commitment monitored against a timeline. Arizona has its own version of that construction complexity. Hundreds of subcontractors, thousands of compliance checkpoints. One failed inspection delays the critical path. The first fab achieved high-volume production in the fourth quarter of 2024. 4-nanometer chips, made in America. For the first time in years, some of the world's most advanced logic chips were being produced at scale on U.S. soil. Apple was identified as one of the customers expected to use wafers manufactured in Arizona. A company that had never sourced advanced processor wafers from an American TSMC fab was now preparing to buy American-made wafers. That milestone landed quietly. The engineers knew what it meant. Now Fabs 2 and 3 are rising. Fab 2 is being equipped for N3 production, targeted for the second half of 2027. Fab 3 is planned for N2 and A16 production by the end of the decade. Initial construction work on Fab 4 and the first advanced packaging facility began in early 2026. Fabs 5 and 6 remain part of the longer-term campus plan, each one more advanced than the last. The $265 billion announced commitment does not stop at construction. It includes tooling, staffing, qualification, ramp, and additional planned expansion beyond the original 6-fab campus. Years of work after the concrete dries. Monitoring never stops. Sensors embedded throughout every critical system. Vibration, temperature, particle counts, power quality. The factory watches itself breathe. Industry analysts have described investments like this as a form of strategic resilience and economic deterrence. That framing matters. This is not just a manufacturing investment. It is infrastructure for national security. Chips made in America are less vulnerable to a blockade or disruption in the Taiwan Strait, although they still depend on a global network of materials, equipment, and packaging suppliers. The strategic calculus behind this factory is as precise as the engineering inside it. Every fab added is another layer of resilience. 6 fabs, 6 lines of defense. Workers are already running shifts in Fab 1. Wafers moving through process steps developed over decades in Taiwan, now executed in Arizona. The desert floor that held nothing a decade ago now holds one of the most advanced manufacturing facilities in the United States. Engineers walk the fab floor every morning, checking yields, reading sensor data, adjusting. This factory became a neighborhood. Thousands of engineers living within miles of the site. building careers that did not exist here before. Wafers produced in Phoenix are now entering the global supply chain and the devices it serves,